AMC, problem 23. And we're looking at this problem here that says Rodrigo has a very large sheet of graph paper. First, he draws a line segment connecting point 0.04 to point 0.20 and colors the four cells whose interior intersects the segment as shown below. Next, Rodrigo draws a line segment connecting the point 2,000, 2,000, 3,000 to 5,000, 8,000. How many cells will he color this time? So he's connecting these 2 points, and we want to find um how many cells that this line goes through. So this seems like a pretty complicated problem if you haven't seen one like this before, but this is pretty common in competition math. It'll probably pop up pretty often. So I'll show you how to do this. What I'm going to start by doing is just simplifying the problem down a little bit. So instead of 2,000, 3,000 to 5,000, 8,000, I'm just going to move this entire line to the so that this point lies on the origin instead. So I would make 2,000, 3,000, 0, that I would make 2,000, 3,000, 0, 0, just to make it a little bit simpler. And doing this is I'm just shifting it over to the left by 2,000 points and down by 3,000 points. So I have to do the same thing to 5,000, 8,000. So we're just shifting this line. So this is now 3,000 and 8,000 minus 3,000 should be 5,000. So I'm not changing the line in any way, and I'm just shifting it over. So it's just a little bit simpler. And now here comes the difficult part. And you're probably asking, how do we find the amount of cells that this line crosses over? So I'm going to start with like a few case by case scenarios and show you the general formula to solve equations like this. So when we look at this original example that the problem gives us, we see that it crosses over 4 cells and it hits this one point, right? It hits this one lattice point, right? So that it doesn't cross over any cells when it crosses over this lattice point. So here we can see that it crosses over 4 cells. And one thing that we can see is that every time we move over one or we go up one, it seems to add a cell, except for when it crosses over this lattice point. I don't know if I'm explaining this very well. I have this 3x5 grid here too that I can show you an example of. And this is especially good since we're looking for a 3,000, 5,000 case. And if I connect these 2 corner points here, we can see that here it doesn't cross any lattice points. So it hits like all of these squares here. They're supposed to be squares, they don't look like them. So we have 1, 2, 3. Oh, sorry, I missed that one. 4, 5, 6, 7. And it seems that when we go up, right? We go up one, we add a square. We go to the side one, we add a square. We go up one, we add a square. We go up one, we add a square. We go side one, we add a square. We go side one, we add a square. So it seems like we go up 5, we add a square, and we go side 3, we add a square, right? But we here only have 1, 2, 3, 4, 5, 6, 7. We don't have 8, right? Which seems a little bit confusing, but then we know that we start with this one square that seems a little bit to be like a communal square where we start with already on the square and we're already occupying a square. So this can be factored into the up and side. I don't know if I'm explaining this very well. But so instead of when we go to the side, right, we can just count this as part of the 5, right? So we go up, 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 5. And we've already counted this square. So we go to the side 1, we go to the side 1. I'm not sure if this is making much sense, but when we do 5 plus 3, we should subtract 1. So the general formula for this type of problem here is if we have m cells going in one direction, so in this case it was 3, and n cells going in another direction, in this case it was 5. So we have m and n. We do m plus n minus the GCD of m n. This means greatest common divisor. So in the 3, 5 case, the greatest common divisor of 3 and 5 was 1 because 3 and 5 share no other common divisors. However, in this case here, where we have 2, 4, our answer should have been 2 plus 4 minus the GCD of 2 and 4. Well, 2 and 4 are both divisible by 2, right? The greatest common divisor of 2 and 4 is 2. So we subtract 2 and we get 4, which is what's in this picture here, right? And I guess another way to think about it is in when we have this lattice point here, it's because we can divide these points and get another point that lies on the same slope, right? This point was 1, 2, and that's because our slope here was 1 over 2, right? And we can hit another lattice point, thereby missing another square here that we would have originally had if they had a GCD of 1 instead of 2, right? And because they have a GCD of 2, they hit one less square. So this might be a little bit confusing, but I think it's important to remember this general formula and a little bit of the thought process that went behind finding it. So now that we know this, we can look for the answer to this 3,000, 5,000 problem. So we start with 0, 0, we go to 3,000, 5,000. So our m and n, this should just be m and n. So it should be 3,000 plus 5,000 based on the formula minus the GCD of 3,000, 5,000. Now, the GCD here should be 1,000, right? Because 1,000 divides into both 3,000 and 5,000, and we can't go any higher. Like, we can't do anything else because when we divide 3,000 by 1,000, we're left with 3, and 5,000 by 1,000, we're left with 5, and 3 and 5 don't have any common divisors besides 1. So our GCD should be 1,000. So our answer should be 8,000 minus 1,000, which equals 7,000. And our answer is C. Let's check. Yep. All right. Thanks, guys.